The educational significance of the stage of reinforcing new material by presenting students with learning tasks is very hard to overestimate. Because in reality, we must always keep in mind the possibility that the student at the stage of first acquaintance with the new topic, to put it mildly, did not fully understand and skillfully manage to hide their lack of understanding. This can happen for completely different reasons, including, by the way, because all students have different cognitive learning styles, and some of them lean more towards understanding through practice, through realizing how it works. And essentially, this stage of the educational process, which works on reinforcement, on deeper understanding of the possibilities offered by the new tool, is actually very valuable when the teacher devotes significant attention to this stage. Tries to design an assignment for students in such a way that it strengthens the understanding of new material and ensures speed, immediacy, self-evidence, and flexibility in using the newly mastered tools. This, of course, requires good methodological preparation in teaching this particular discipline and, generally speaking, significant effort. Because if we are talking about school education, there are many methodological materials that a teacher can use. As for university education, in this case, the academic disciplines are not as well provided with materials for reinforcement carefully verified and created by entire scientific teams. Reinforcing new material with special tasks is beneficial because it requires maximum student activity, who is forced to seek initially hidden possibilities, unlike the relatively clear presentation of lecture material by the teacher. And in this regard, I would like to draw your attention to the difference between a mathematical problem as such and the so-called educational mathematical problem. By a purely mathematical problem, its direct product is understood as obtaining a certain mathematical fact. Well, for example, when extracting the root of an equation, constructing a graph of a function, or establishing relationships between geometric figures. In an educational problem, it is important to realize that its direct product is not the solution itself, but rather some educational fact, some educational achievement. That is, first of all, it is deepening knowledge, practicing certain skills, refining mental operation. For example, organizing educational work, say, on proving a certain theorem, should include stages of motivation, hypothesis formulation, statement formulation, and proof search. Moreover, teaching proof can be done, for example, using a text with gaps. That is, everything should be methodically verified, and the teacher usually decides on a set of hints or leading questions that will work towards the specific methodological goal set at this stage. Well, in the case when such a methodological goal is not thought out in advance, then we are simply talking about a mathematical problem, nothing more. But overall, the educational task is aimed at the student discovering some invariant in its method of solution, which more often, of course, turns out to be normative, known in advance. And then such educational tasks will be reproductive for most students, but certainly very useful at this stage for practicing a particular skill. Well, the development of educational tasks with more ambitious, perhaps, goals concerning the student's mastery of more flexible ways of recognizing the most relevant tools available in their arsenal. As a result of mastering not only the specific new topic, but also the completed program as a whole. The work on developing this type of tasks requires the teacher not only to have a higher level of methodological skill, but also perhaps a higher level of patience, because it is expected that students will have a hard time mastering such tasks. But it should always be kept in mind that in pedagogy, immediate results are rarely achieved as we would like. This applies not only to the process of upbringing, but also to the process of education. For some time expected from students, the level of expertise will not manifest itself because in reality the desired flexibility in using the still forming structure of the course material has a cumulative nature, and especially in the early stages it is weakly manifested and weakly recognized, due to the fact that the thought process has a multi-layered structure. Part of it is not accessible to consciousness and gradually accumulates, inevitably leading the student to increased potential. In this context, I would like to recall a theory such as connectionism or the theory of parallel distributed processing of information, which can give us an understanding about how it happens that in addition to the conscious product, the thought process also has a certain side accumulative effect. In fact, you are likely familiar with this theory, which began to be developed in the middle of the last century because the metaphor of cognition presented in it is described through processes of parallel information processing by a network consisting of neurons. These networks are organized into several layers and levels. Connections between these conditional levels of neurons have different weight coefficients. From here, we arrive at the backpropagation algorithm and so on. That is, as you understand, such processes have a gradual cumulative effect which leads the student either to some insight or simply to the improvement of their skills in operating with the acquired knowledge. It is also useful for us to know that in a generalized way, the sequence of thought processes for solving problems can be represented as such universal and usually sequential operations as firstly selective encoding. That is, as they sometimes say, determining the solvability or unsolvability of a problem. Selective comparison. I would say that this is the application of mastered methods and algorithms to the specific conditions of the given task. And what is most valuable for us is the inclusion of selective combination. The case when a student is able to flexibly use the learned material, correctly performing its analysis, synthesis, abstraction, and categorization, regardless of how long ago it was learned. After all, this will indicate a good structuring of the acquired knowledge, a good degree of consolidation and integration of new material. I would like to mention one more thing. Throughout the course, it was often emphasized to you that it is extremely important to adhere to the principle of spaced learning as it aids in memory consolidation. But there is another approach in pedagogy that further develops the idea of interval learning. This is the so-called practice of interleaving. What is the essence? There is the idea of the so-called block system of learning, where we start each new topic, master the new material of this topic, and in the process of practice, solve problems focused exclusively on this topic. However, the idea of interleaving suggests that a more effective approach is to include tasks from previous topics in the pool of assignments when working on a new topic. But this, of course, is alongside those necessary comprehensive tasks, the value of which I clarified for you in this lecture. That is, those that allow strengthening the connection of the new topic with the material already studied. In other words, it can be very useful, not as a priority, but consistently to include in the list of tasks not only those related to the new topic, but also tasks that require recalling knowledge from previously studied topics. In general, the experiments that were conducted regarding this idea interleaving showed that if one group learns through a block system and another through a program that actively uses interleaving, the first group performed better on the topic if testing was conducted immediately after the study was completed. And the second group consistently showed much higher results during the final assessment across all topics.